Hi everyone, Katie here again for the second lecture. Today we're going to talk about linear regression as it's applied to operational oceanography, or in this case, practical biogeochemistry. Today will be all about constructing a calibration curve and estimating uncertainties in calibration parameters. So this is the bedrock foundation of essentially all of the analyses you're going to do, particularly all of the nutrient analyses. The job of a marine analytical chemist is to ensure that the sample you collect is representative of the properties of the study area, because obviously you have a limited ability to collect samples when you're at sea, and that the sample keeps the properties of interest from the point of collection to the final analytical measurement. So going out on a boat, collecting a seawater sample, and then having something change in that seawater sample before you analyze it is not very useful, right? You need to ensure that it can retain whatever the properties of interest are. So the way that you collect it, the way that you store it, the way that you go about measuring it, all of these things will be to try to retain the integrity of that sample. There's some good guidelines you can find online for the process of selecting, collecting, preserving, transporting, and storing samples. And this is important, particularly, for example, on expeditions that are on the Agulhas Tube, for example. A lot of the analyses that you'll want to do, you won't be able to do until you get back to the lab. And so on a 3-month cruise, that could mean you collect samples on the first week of the cruise, and you need to maintain the integrity of those samples for the following 3 months until you get back to shore. So you need to be aware of what it is you want to measure, how you should go about strategizing how to sample that, what equipment needs to be used, what kind of storage, how they need to be preserved, and then also the sample size. You're not going to run out of seawater, although you will have to share, but at some point you have limited freezer space if, for example, you need to freeze samples. And so all of these things need to go into designing your strategy. The other thing to keep in mind is what's the aim of the study. So depending on the scientific question you're trying to address, maybe 2 or 3 sampling sites is fine. And maybe sampling frequency of once a year or opportunistic sampling is fine. But if you're looking at something like investigating spatial or seasonal variability, you might need significantly more sampling sites. And you might, or let's say you're just looking at spatial variability, you might not care when the samples are collected, but you want to make sure you get enough sites. If you're interested in seasonality, you might have less interest in where the samples are from, but you might be really concerned with the frequency at which you can sample. So you might want to choose somewhere that you can get back to fairly easily. So there's lots of things to think about. You have to think about where it is, what your study area is like, what the actual point of your scientific investigation is, the location and number of stations you'll be able to access, what the vertical resolution is that you need through the water column is. And that includes having some sort of beforehand knowledge of what the vertical resolution looks like. You need to know the depths and frequency of sampling and what the suitable sampling techniques are. Now, of course, in this case, because the resources that we use in oceanography are shared, you might not necessarily always get to pick the exact depths or sampling locations. And so you have to also learn to compromise and share water with people in the hopes that everyone's groups can accomplish as much science as possible. A couple of things to keep in mind. So if you're in a bay or a harbor or coastal waters, like you will be for your field trip, you can usually get a high density of stations, and you can sample often because it's not difficult to get to. But you have to remember that there could be things like tidal changes, local effects, human activities, hydrological conditions, that all of these things might influence your sampling. Whereas in the open ocean areas, you've got to keep in mind that you have really high horizontal homogeneity. So once you're in the gyre of the South Atlantic, you have to cruise for a long time to get out of it. But vertically, you have a lot of heterogeneity. So you're going to need a much higher vertical sampling resolution than you do a horizontal sampling resolution. Horizontally, your stations may be separated by hundreds of kilometers. But vertically, of course, your samples are going to be separated by maybe 50 meters, 100 meters at the top of the water column, getting through to higher vertical separation as you go down into the water column, right? As your water masses become larger and stratified with different properties. And of course, you must keep in mind the random and systematic errors that I introduced in the previous lecture. So there's these things called SCORE working groups. Might be interesting if those of you aren't familiar with them to Google SCORE, the Scientific Committee on Ocean Research. And there's a working group on nutrients. And so this is a group of people from around the world who do intercomparison studies. So they take the exact same samples and they get mailed out to all the groups and everyone measures them. And in theory, everyone should report back the same number. And they use certified reference materials to do this, which we'll talk about a little bit more later. And so what type of error, if you think about what we learned before, this process is trying to eliminate systematic errors, right? That might be occurring because there's just an error in the laboratory measurement. Now, the second thing would be, let's say the CTD consistently fires at the wrong depth. So every time you think you're firing at 5 meters, it's actually firing at 8 meters. Or the ship discharges water or waste just before sampling. So these would be examples of, the first one would be probably almost a gross error, depending on what you were calculating, but again, a systematic error. Whereas the second would be a random error. If the CTD randomly fired at wrong depths, like sometimes it was a bit low and sometimes a bit high, then that would be a random error, right? And there wouldn't be much you could do about that. Okay, so certified reference materials are really important. We use them a lot in all the different analyses we do. And these are specially prepared samples that contain a particular analyte. So you might have a certified reference material for nitrate, and you'd have a different one for silicate, for example. The concentration of that species has been predetermined to an incredibly high degree of accuracy and precision. And you get a certificate when you buy a CRM. They're very expensive. And it gives you this in detail. And so if you're using, for example, seawater samples, you'd want to get a certified reference material that was prepared in artificial seawater, or something that's similar to what you're actually going to be analyzing. And this can allow for accuracy across laboratories. So let's say you and I go and we collect a bunch of seawater, and I go back to my lab and I measure nitrate, and you go back to your lab and you measure nitrate. And for the exact same samples, we report different values. Well, it's very difficult to actually figure out which one of us is right and which one of us is wrong. But if we both measure a certified reference material, then it's easy, right? Because I measure the sample and I get a value of 10, and you measure the sample and you get a value of 15. Well, if we both measure the CRM and we have that little piece of paper, that certificate that says the CRM is exactly 50, and I get a value of 50 and you get a value of 60, then we know there's a problem, right? That overestimate in your sample analysis, you're also doing that same overestimate in the CRM. And so there's a problem with that measurement in your lab. So certified reference materials really help you get at really giving you confidence that your accuracy, not precision in this case, this is about accuracy, that your accuracy is as high as possible. So the other thing to keep in mind is quality control and quality assurance. And they're not exactly the same thing. QC is how you achieve quality or how you regulate the mechanism that's happening in your lab. Quality assurance is a system of procedures that you put in place to make sure that the QC actually happens. So QA is more of a system. So this can be proficiency testing of the laboratory, or in our case, the use of certified reference materials. Blanks are another really important component to biogeochemistry labs. So you need a procedural blank. And so this is a sample. So you collect a bunch of seawater samples, and at the same time you collect an extra sample. Now the seawater samples that you want to measure, you probably have to add all sorts of chemicals to, put them through the reaction process, right, in order to actually get at the answer. And your procedural blank is everything else, but it doesn't actually have any of the analyte in it. So in this case, your procedural blank, in order to get a procedural blank, you'd use just plain water, for example. The other kind of blank would be your instrument blank. So there's going to be some signal that you're measuring with your instrument that's inherent to the instrument itself. And again, you can use DI water or air to get at this. The third thing you have to keep in mind are matrix effects. So it's not always exactly straightforward to decide what kind of blank you should use. So for example, when you're measuring ammonium concentrations, we make a standard curve where we have known standards of ammonium, but we prepare them in fresh water, whereas the samples we collect are actually in a seawater matrix. And so the fact that our standards are in a different matrix than our samples actually causes a problem, because the presence of the salts and the organic matter can interfere with the fluorescence in the instrument, but our standards aren't reflecting that because there are no salts or organic matter in our standards. And there's a way you can deal with that. So the matrix effects, like I just said, they're caused by substances other than the analyte, other than whatever it is you're trying to measure, and they can either suppress the signal or intensify the signal. So accounting for matrix effects is really important because they can vary through space and time in natural waters, whatever it is that's giving you the matrix effect. And so you could be seeing a variation in your samples that actually has nothing to do with the analyte of interest, ammonium in this example, and might just be because you're going through a transect where pH is changing or dissolved organic matter is changing. And the way we get around this is with a standard addition method. I'm not actually going to go into detail on standard addition method, but it's in the readings if you guys are interested. So the limit of detection is the lowest concentration level that is statistically different from a blank within a specified confidence level. So this limit of detection issue has to do with whether or not you can actually measure something. So sometimes a species is so low in concentration in the ocean that you actually can't measure it using a given method. And so when you're selecting a method, you need to have some sense of what concentration range you're expecting so that you know if it's possible to make the measurement. And you can determine this on whatever instrument you're measuring. And it has to do with the relationship between the instrumental noise, so however much background it has, and how large the analyte signal is. And in this case, it's the average value of the blank. So when you just measure DI water, let's say you're interested in ammonium. So in this case, you take DI water that has no ammonium in it, and you measure it on the instrument, and you see what the instrument tells you. And so it's the average of that plus 3 times the standard deviation of that blank. And so in order to actually generate a real signal, to make a real measurement, the concentration of the analyte has to be at least as high as that limit of detection, and obviously preferably higher, right? Okay, getting to calibration, which is the basis of what we're doing here. A calibration curve is the response of an instrument as it relates to the concentration of the analyte of interest. And so you choose the concentrations of your calibration curve yourself, and these are the independent variable. And whatever the instrumental output is the dependent variable. Calibration models are almost always linear and univariate, so it's some concentration and some output. And depending on the instrument you're using, it could be peak height, peak area, potential current, absorbance, etc. Most of the ones we work with are going to be absorbance. And the calibration essentially relies on a linear model. Basically, the equation of the line is what we're going to be dealing with here. And so Y is the instrument response here. X is your concentration. And then A and B are the coefficients of the model. B is the slope, which is a measure of the analytical sensitivity in this case. N does have units. It has units of whatever Y is over X. And A is the Y-intercept, which in this case is an indication of the blank. So what is the response of the instrument when X, the concentration of the analyte in question, is 0? And it's important to remember that any given measurement of Y, denoted here by Y sub I, that should be Y sub I, is subject to some sort of measurement error. This should be epsilon sub I. So the given measurement of Y is the actual value plus some error, and that error in this case can be positive or negative. And you can extend that out. So a given measurement of Y is equal to the intercept plus the slope times the concentration plus that error. So basically the idea is you use your calibration curve to figure out what A and B are to get the equation of the line, and then you measure a sample that has an unknown concentration. So you measure a sample and you don't know the concentration, but you know what the instrument response is. And so you can calculate the concentration from the calibration. So we're going to throw through this step by step. There are a bunch of assumptions in the basic linear model. So you assume that the response of the instrument varies linearly with concentration, and that's usually based on good foundation. You also assume that all of the uncertainty resides in the dependent variable Y, and that uncertainty is normally distributed. So that means basically that this model assumes that you made your standard concentrations absolutely perfectly and there's no error there. It also assumes that the data are homoscedastic, meaning that the errors in the Y value are independent of the concentration. And this is important, and it's an assumption that's frequently broken. So if you have a relative standard deviation of 2% across a range of concentrations, for the high concentration standards, that's not a big deal. The standard deviation of a 1 millimolar measurement will be 0.02 millimolar. But if you have a measurement of a 0.1 molar standard, it's 2 millimolar, right? So it's much higher for higher concentration standards. The problem with these assumptions is that when you plug things into programs like Excel and R, they assume that all of these assumptions are valid and that they're true. Okay, so there are some practical steps here. The first is to obtain calibration data, which you'll be learning how to do in the lab. So we will simulate some calibration data for you. So you made a series of concentration standards with this range of concentration. So you went into the lab and you made 6 different concentrations. So you made 6 different vials of standards with these concentrations and you measured their fluorescence, and this is what the instrument gave you. Okay, so you obtained calibration data. That's the first step. So the first thing you want to do, well, you can plot it first. You can see here you've got concentration on the x-axis and fluorescence on the y-axis, and it's looking quite like a straight line, so that's a good first step. But the first thing you want to do is calculate R and R squared. And I've got in parentheses here, even though this is mostly useless in this context. Well, you still do it, but I'll explain in a moment why it's mostly useless. So anything that is sort of supposed to end up in a straight line or that you're using as a calibration, you can evaluate in terms of the correlation coefficient. And this describes how close the data lie to a perfect straight line. The Pearson correlation coefficient R has values from 0 to 1. And a value of 1 would be perfect. It would mean that every data point falls on a perfect straight line. And R itself is typically very close to 1, which is why we report the R squared. But why is the R squared useless? So in this case, you can calculate the R squared for this data. It's 0.9997. But it doesn't really tell you much about the quality of a regression. It's the fraction of the variance in the dependent variable explained by the relationship with the independent variable, which is another way of saying that we chose this method because we knew the instrument would respond linearly with concentration. So it's already built into the assumption. If you couldn't get a good, really high R squared value, you wouldn't be using this analytical method. Because if you couldn't get a good high R squared value, it would mean this method doesn't work, which would mean it would have been kicked out of your scientific option toolkit a very long time ago. And so really, it's just kind of a first test to make sure things are going fairly well. And for any calibration to proceed, your R squared needs to be at least 0.9, but really for the kind of linear, like basic spectrophotometric measurements we're making, you should be able to get 3 nines out of it. Okay, so you've estimated the sort of useless one, and now you can move on to getting the slope and intercept. So the way you find the best split line through the data is the least squares method for deriving a calibration line. And you can see here you've got y bar, which is the average of all your y values, equals the slope times x bar plus a, where x bar is the average of all your x values. So first you calculate the slope b, and then you've got, these are the equations here. I put them on because people don't usually frequently look at them. But this is what's actually happening in the background. So first you calculate the sum of squares of xy and the sum of squares of xx using these formulas. And then once you get the slope, it's fairly straightforward. You know y bar, you know b because you just calculated it, you know x bar, and then you calculate a, the intercept. So for this calibration set, we've got our r squared, our slope, and our y-intercept. The relationship between the instrument signal and the concentration is essentially what your slope is giving you. And don't forget that your slope and y-intercept have units. These are not, whoops, These are not unitless numbers in this case. The slope is y over x, which means it's fluorescence over concentration. And your y-intercept is actually on the y-axis, so it has units of fluorescence units. Okay, the next step that a lot of you, at this point, you guys might not have done much of these sort of next steps, is to look at the residuals of y against x. And so a really good calibration has residuals that are randomly distributed about 0. And what the residuals are is once you get, so you have the data, you measured x and y, and then now you know the slope. So what you can do is, instead of using your measured fluorescence value, which is this column, you can say, given the concentration and the slope and intercept I just calculated, what should the y value be if this data point fell completely on the line? And so in this case, it would be, for example, if this was 0.723, was this number here, you would plug the 0.25 micromolar into your line, and you would calculate that it should be 0.7109. That's this value if it were actually on the line. And then you can look at the difference between these two numbers. So basically this y value minus this y hat value gives you this residual value. And then you plot these residuals as a function of concentration, and that's what we're looking at here. And you can see you've got a 0 line here. So it should be, if the errors are random, you should have some that are above and then some that are below. And so this helps you see what's happening with your regression. And so some examples that you can see here, if you look at the left, this is an example of good residuals because you have some values above the line and some values below the line, and the distance from the 0 line is fairly uniform. Whereas in this example B, these are not good residuals because what you see here is as your concentration increases with higher standards, the error gets bigger. So this distance from the 0 line is getting bigger. So your error is actually a function of your concentration. That suggests that you have some sort of indeterminate error affecting things, and that your concentration, the signal, is not just dependent of the concentration. There's something else going on. And in this last example, in example C, you can see that these errors don't really look random. There's a pattern here. You know, you can pretty easily draw a line through this. And so this suggests that you don't actually have a straight line relationship. And you would use a different sort of approach for this kind of regression. So plotting the residuals is much more useful than looking at an R-squared value for actually knowing if your calibration is going well or not. Okay, so next step is you calculate the standard deviation of y on x. And so this is the standard error of the regression. And so in this case, this is a value you want to minimize. If your calibration is going really well, you want a small standard error of the regression. And in this case, it has the same units of y. So if you look here, if your data fit the equation perfectly, then your residuals are all 0. And this right here is a measure of your residuals. So if your residuals are all 0, and you square that, you get 0 divided by a number, you end up with a standard error regression that's equal to 0. That would suggest that everything is perfect. So in this case, you can calculate for this data set, it's 0.034. Okay, the next step is the slope value you calculated has some error associated with it. It's not just one number. And so you calculate the error in the slope, and you can use this, the easiest way to present this is with a confidence interval. And so this is B is the slope, S indicates it's the standard deviation of the slope. And so you calculate that using this equation, and then you report your slope, which was 2.526, and then you use a confidence interval. So it's this calculated standard deviation times the value you get from a t-table. In this case, we've chosen 95% confidence interval. And so you would report that your slope is 2.526 plus or minus 0.065. So it gives you a sense of how accurate your measurement of the slope is. We do the same thing for the y-intercept. So A is the y-intercept. This is the equation to calculate the standard deviation of the y-intercept. So you report your y-intercept here, and then you do your t-value times the standard deviation. Again, we've chosen 95% confidence interval. So here you would say your y-intercept is 0.079 plus or minus 0.075. So in this case, it's actually fairly high uncertainty associated with your y-intercept. Okay, next up you want to make a plot, which you probably would have already done. You can see here we're building our statistics table on the right. And then the last thing you want to do is the whole reason for this. So the whole point of doing all this is because you have some samples and you don't know what their concentration is. And so using those regression statistics, you can calculate the concentration of your unknown samples. And as importantly, you can calculate the standard deviation of your estimate of that concentration. So you know the slope, you know the y-intercept, you know y0 is what you measured for your unknown sample, and you can calculate x, which is your concentration. So your unknown concentration equals the measured response minus the y-intercept divided by the slope, all right, where the y-intercept and slope come from your linear regression model. The other thing that you want to do once you calculate the concentration is you want to know how well do you know that concentration. So you want to report some error, or in this case, the confidence interval. And so x hat is the concentration you just calculated for your unknown sample, and there's a standard deviation associated with that. So if you look here, you can see the standard error of regression divided by the slope multiplied by this here. Useful things here to see. So one reason to minimize the standard error of the regression is because it's directly related to the standard error that you have to report. So if you have a smaller number here, it keeps this standard deviation low. If you have a large standard error of regression, then this value becomes higher. Similarly, looking at this equation helps you think about what the slope is. When you're looking at a method, you actually want the slope of that method to be quite large, because the larger b is, the smaller this error will be. Other things to look at, if you have more calibration points, which is n, okay, so n is in the denominator, so more calibration points keeps this value down. And the other thing is, if you measure your sample, you never measure your sample just once. So the more you measure your sample, right, the larger this number is, it also pushes this error down, okay? So looking at this equation, the standard deviation of what you can report for the unknown concentration helps you sort of understand how the various parts of what you're doing with your calibration impact the standard deviation of your measurement. Okay, so for example, you've gone out and collected a sample, and this seawater sample is measured, and it has a fluorescence of 0.722. So that's your Y0 value. So you take that, you use your slope and your y-intercept, and you can calculate that the concentration of that sample is 0.255. And if you look at your linear regression, this makes sense. 0.722 is a very low value. It's less than 1. If you go across to the line and go down, you get something that's about 0.255. That makes sense. Then you also can calculate the error of that concentration. So using the equation in the previous slide, the standard deviation of that is plus or minus 0.016. So some good practice guidelines for calibrations, because obviously you need to make practical decisions about how many standards you're going to run and what are the concentration of those standards going to be. You want to choose the shortest range possible for the likely range of unknown samples. So one thing to think about is, in the ocean, a lot of times your surface samples will have very different nutrient concentrations than your deep samples. And so it might be better to run all of your surface samples together with one standard curve and then all of your deep samples together with a second standard curve. You also want to make sure you have sufficient concentrations to cover the range and get a suitable confidence interval on your measurements. And you want to evenly space the concentration throughout the calibration range. Practically speaking, you almost always use a 5-point calibration curve plus a DI blank. You're supposed to make your calibration solutions independently, but we almost always make serial dilutions of a stock. And then the other thing is, if you make a calibration curve and you measure it and you don't look at any of the statistics, you could really be wasting your time. So make a calibration curve and then look at the residuals, calculate the regression. And if you have to, if it's not looking good, remake your standards. Because you will have seawater samples, like for example, if you collected seawater from a Southern Ocean cruise, you can't just go back and get more of that water. And so you don't want to actually start your sample analysis until you know that your calibration is looking pretty good. And so that's really important. And I know a lot of this might seem really foreign at the moment, but I promise you, once we get into the lab and you start generating your own calibration curve, this is all going to start to make a lot more sense.